What if the universe has been trying to talk to us this whole time, and we just didn't recognize the language? Out there, scattered across the vast darkness of space, celestial objects called pulsars spin with eerie precision, sending out beams of radio waves that sweep past Earth like clockwork. These cosmic metronomes have fascinated scientists since their discovery. But what if their rhythmic pulses aren't just natural phenomena? What if, hidden in their precise ticking, there's something far more extraordinary, a message we've been missing? Think about it. For decades, we've treated pulsars as celestial oddities, their signals catalogued and studied as mere quirks of physics. But consider how eerily perfect they are. Some pulse with such regularity, they rival the accuracy of atomic clocks. Others emit patterns so complex, they defy simple explanation. Could there be more to these cosmic lighthouses than meets the eye? The idea isn't as far-fetched as it sounds. Some researchers have dared to ask, what if pulsars aren't just dead stars doing what dead stars do? What if their signals are intentional, a galactic SOS, a beacon from a long-lost civilization, or even a test to see if anyone's listening? This is where the story gets thrilling. We're not just talking about abstract astronomy here. This is about redefining humanity's place in the cosmos. If even one pulsar's signal turned out to be artificial, it would shake science to its core. It would mean we're not alone, and that the universe is far stranger, far more mysterious than we ever imagined. So buckle up. Over the next few minutes, we'll journey through the cutting-edge science of pulsars, explore the boldest theories about their origins, and confront the spine-tingling possibility that we've been overlooking cosmic distress signals for generations. The question isn't just what pulsars are, it's why they're here, and the answer might change everything. Pulsars are the universe's most precise timekeepers, cosmic lighthouses spinning in the void with such unwavering rhythm, they make Swiss watches look unreliable. These bizarre objects are born from the violent deaths of massive stars, collapsing into neutron stars so dense, a teaspoon of their material would weigh 1 billion tons on Earth. But what truly sets them apart is how they behave. Picture a lighthouse beam sweeping across the ocean, only instead of light, it's a blistering pulse of radiation, and instead of water, it's cutting through the emptiness of space. When that beam crosses Earth, we detect it as a radio pulse, a blink so regular, early astronomers joked it might be aliens signaling us. That playful nickname, Little Green Men, stuck for a reason. The first pulsar discovered, later named CP191919, had pulses spaced just 1.337 seconds apart, unnervingly precise, as if engineered. Today, we know of pulsars that spin hundreds of times per second, their beams flickering like strobe lights with mind-boggling consistency. The fastest, called millisecond pulsars, are so stable they lose only a second over millions of years. But here's where it gets eerie. Buried in that precision might be layers of complexity we've barely begun to untangle. Take the Crab pulsar, for example. It doesn't just tick like a clock, it occasionally hiccups with sudden glitches in its rotation. Then there are pulsars emitting dual frequency beams, or those with pulse patterns that drift unpredictably. Could these variations be cosmic static, or might they carry something deliberate? Scientists have even found pulsars in binary systems, their orbits so meticulously balanced they rival the finest human-made instruments. It's as if the universe is showing off or leaving breadcrumbs. The real puzzle isn't just how pulsars work, but why they're so perfect for communication. Their signals travel across galaxies with minimal distortion, piercing through cosmic dust and magnetic fields that scramble other transmissions. They're loud, clear, and persistent qualities you'd want in a beacon designed to last billions of years. Whether that's a coincidence or a clue, one thing's certain: the deeper we listen, the more the universe seems to be whispering in a language we're only starting to learn. At their heart, pulsars are the spectacular remains of stars that once burned bright before collapsing in violent supernova explosions. When a massive star runs out of fuel, its outer layers blast outward in a brilliant burst of energy, while its core crushes down into an unimaginably dense neutron star, just 12 miles across, yet packing more mass than our entire sun. Spin these remnants at dizzying speeds, add a magnetic field trillions of times stronger than Earth's, and you've got the recipe for a pulsar, a cosmic powerhouse firing twin beams of radiation from its poles like a spinning lighthouse in the dark. For scientists, these beams are a gift from the universe. Their clockwork precision makes them ideal tools for testing the very fabric of reality. Take Einstein's theory of relativity. Pulsars in binary systems have allowed researchers to observe how their intense gravity bends space-time, confirming predictions made over a century ago. Some spacecraft even use pulsar signals as galactic GPS, triangulating their position in deep space by locking onto these distant beacons. But here's the catch: not all pulsars follow the rules. Every now and then, a pulsar stutters. Its rhythm falters just for a fraction of a second before resuming its usual beat. Astronomers call these disruptions glitches, and while most can be explained by starquakes or sudden shifts in the neutron star's interior, others remain stubbornly mysterious. The Vela pulsar, for instance, experiences glitches that cause its spin to speed up abruptly, as if something inside it suddenly unlocked. Then there's the case of PSRB 1937+21, a pulsar so stable it's known as the millisecond pulsar, except for that one time it hiccuped without warning, leaving scientists scratching their heads. The unsettling truth is, we still don't fully understand what's happening inside these ultra-dense objects. Could their anomalies be the result of exotic physics, like vortices of superfluid neutrons sloshing beneath their crusts? Or dare we consider it, might there be patterns in the noise, subtle deviations that don't fit the expected chaos of nature? When a signal pauses, stutters, or shifts in a way that defies models, it forces us to ask, are we seeing the limits of astrophysics, or the faint traces of something far more extraordinary? The universe rarely leaves us with easy answers, but sometimes it leaves us with clues. For decades, the search for extraterrestrial intelligence has operated on one core assumption: that any civilization advanced enough to reach out would do so with clear, unmistakable signals. SETI radio telescopes have spent years combing the cosmos for narrowband transmissions, the kind a technological society might produce deliberately. But what if we've been listening for the wrong thing? Imagine an alien civilization wanting to send a message across interstellar space. They'd need a signal powerful enough to travel light years, distinct enough to stand out from cosmic noise, and enduring enough to last millennia. Pulsars, ironically, check every box. Here's the twist: SETI filters are designed to screen out natural interference, including the broadband bursts from pulsars. It's like tuning a radio to ignore static, except what if the static isn't static at all? Some scientists speculate that an advanced society might piggyback information onto pulsar-like signals, using the star's natural energy as a carrier wave. After all, why build a transmitter when the universe provides one for free? A pulsar's beam could act as a cosmic envelope, hiding data in slight variations in pulse timing, polarization, or even those mysterious glitches we can't yet explain. The idea isn't science fiction. Mathematically, it's possible to encode data in a pulsar's signal without disrupting its natural appearance. A study published in the International Journal of Astrobiology even outlined how a civilization could tweak a neutron star's magnetic field to modulate its pulses, like tapping out Morse code on a stellar scale. And if that sounds far-fetched, consider humanity's own attempts at cosmic communication. The Arecibo message, beamed toward a star cluster in 1974, was a crude shout into the void compared to the elegance of manipulating a pulsar signal. If we can conceive of it, why couldn't someone else have mastered it? Critics argue that extraordinary claims require extraordinary evidence, and so far, no pulsar signal has shown undeniable signs of artificial tampering. But absence of proof isn't proof of absence. After all, we've only been studying these objects for half a century, a blink in cosmic time. What's more tantalizing is the possibility that we've already collected the evidence, sitting untouched in decades of archived data, waiting for the right algorithm or the sharp-eyed researcher to uncover a pattern that wasn't supposed to be there. The universe is under no obligation to make its secrets easy to find. But if we're willing to question our assumptions, we might just discover that the greatest messages aren't sent, they're hidden in plain sight. In the summer of 1977, a radio telescope in Ohio picked up something extraordinary, a 72-second burst of radio waves so intense, an astronomer scrawled, "Wow." In the margin of the printout, decades later, the wow signal remains one of the most tantalizing cosmic mysteries, a fleeting blip that vanished as suddenly as it appeared. No one knows if it was a natural phenomenon or something more, but its very existence forces us to confront a humbling truth. The universe is full of signals we don't understand. And pulsars, with their eerily precise rhythms occasionally interrupted by strange hiccups, might be hiding similar surprises. Think about how the wow signal played out a single, powerful transmission, never repeated, slipping through the noise like a whisper in a crowded room. Now compare that to pulsars like Jodrell Banks' lighthouse pulsar, which occasionally skips a beat or emits an irregular pulse. Most astronomers dismiss these anomalies as starquakes or magnetic shifts, but what if they're missing the forest for the trees? If an advanced civilization wanted to signal across the galaxy without draining their energy reserves, wouldn't intermittent bursts timed just right be more efficient than a constant broadcast? The challenge is in the decoding. Human communication relies on repetition and predictability, but an alien intelligence might use patterns we haven't even thought to look for. Take PSRB 0919+06, a pulsar that occasionally goes silent for minutes before restarting with a slightly different rhythm. It's easy to chalk this up to cosmic interference, but consider how much information could be packed into those gaps. Silence, after all, can be just as meaningful as sound. What's fascinating is how our own technology is starting to catch up with these possibilities. Machine learning algorithms now sift through pulsar data, hunting for irregularities that older methods might overlook. In 2018, researchers at Breakthrough Listen analyzed thousands of fast radio bursts, another class of mysterious cosmic signals, using AI trained to spot unnatural patterns. While nothing definitive emerged, the mere fact that we're looking this way is a paradigm shift. We're no longer just listening for deliberate hello messages, we're searching for fingerprints hidden in nature itself. Critics argue that pulsar variations are simply the universe being messy, and they might be right. But history shows us how often science's biggest leaps begin with someone daring to ask, what if we're wrong? The wow signal taught us that cosmic mysteries don't always announce themselves with flashing lights. Sometimes, the most important messages are the ones that don't repeat the ones that force us to question everything we thought we knew about how the universe speaks. And if pulsars are part of that conversation, we're only just learning how to listen. Pulsars are often called the universe's most reliable clocks, but even the finest timepieces occasionally need adjustment, and these cosmic marvels are no exception. While most pulsars tick away with near-perfect precision, a select few exhibit tiny, unexplained hiccups in their rhythm. Scientists call these deviations timing anomalies, and while many can be chalked up to violent starquakes or the turbulent interstellar medium warping their signals as they travel, some stubbornly resist explanation. Take the case of Pulsar J 1843-0463, a pulsar whose pulses arrive just a fraction of a second late every few years, as if something unseen is gently tugging at its rhythm. Or consider Pulsar B 0943+10, which occasionally emits bursts of radio waves so irregular they seem almost deliberate. These anomalies have led some researchers to venture into daring territory. Astrophysicist Paul Davies once floated a provocative idea. What if an advanced civilization could harness a pulsar's immense energy to encode messages? Picture a society so advanced they've mastered the ability to nudge a neutron star's magnetic field, tweaking its pulses like Morse code tapped out on a cosmic scale. It sounds like the plot of a sci-fi novel, but the math holds up. A sufficiently advanced civilization could, in theory, manipulate a pulsar's emissions to transmit information across galaxies. No giant transmitters required, just the natural power of a spinning stellar corpse. The beauty of this idea lies in its subtlety. Unlike the brute force approach of blasting radio signals into space, piggybacking on a pulsar's existing beam would be elegant and energy efficient. A message hidden in the timing glitches of a neutron star could persist for millions of years, surviving long after the civilization that sent it faded into dust. And here's the kicker: we might have already recorded these anomalies without realizing their significance. Decades of pulsar data sit in archives packed with irregularities dismissed as noise. What if the key to unlocking an interstellar telegram has been sitting in a hard drive all along? Of course, skepticism is healthy. The vast majority of pulsar anomalies have mundane explanations: shifting crusts, turbulent magnetic fields, or interference from cosmic debris. But science progresses by probing the gaps, and these unexplained hiccuping pulsars represent some of the most intriguing gaps of all. Whether they're natural oddities or something more, one thing's certain: the universe is far stranger than we've yet imagined. And if we're willing to entertain the wildest possibilities, we might just discover that the cosmos has been speaking to us all along, in a language written not in words, but in the silent, rhythmic pulses of the stars themselves. Binary pulsars take the mystery of these cosmic timekeepers to an entirely new level. Imagine two neutron stars locked in a dizzying dance, whirling around each other at fractions of the speed of light, their gravitational pull so intense it bends space-time itself. These aren't just celestial curiosities, they're laboratories for some of the universe's most extreme physics. Einstein's theory of general relativity predicts their orbits should decay over time as they emit gravitational waves, and in the case of the famous Hulse-Taylor binary pulsar, that's exactly what astronomers observed, earning them a Nobel Prize. But what if these paired pulsars are doing more than just proving Einstein right? Consider the possibilities. A civilization advanced enough to manipulate stellar remnants could use binary pulsars as the ultimate communication array. Think of it like this: the regular pulses from one neutron star could serve as a carrier wave, while its partner's orbit introduces subtle delays or accelerations, a kind of cosmic frequency modulation. The predictable decay of their orbits would act like a built-in clock, synchronizing the message across millennia. Even more intriguing, the gravitational interplay between the two stars could encode information in the warping of space itself, a language written not in radio waves but in the fabric of reality. The beauty of this idea lies in its efficiency. Unlike a single pulsar's beam, which might require precise modulation to carry a signal, a binary system offers a naturally dynamic platform. The periodic changes in orbital timing, the slight wobbles induced by gravitational interactions, these could all serve as data points in a transmission spanning light years. And here's the kicker: we already monitor these systems with incredible precision. Tiny deviations in the Hulse-Taylor pulsar's orbit were measured to within a fraction of a second over decades. If someone were embedding a message in those microsecond anomalies, we might already have the data to find it. We just haven't known where to look. Of course, the leap from could to is enormous. Most astrophysicists would argue that binary pulsars are exactly what they appear to be, breathtaking natural phenomena. But history has shown us that dismissing the extraordinary too quickly can blind us to breakthroughs. After all, the first pulsar signals were nearly mistaken for alien broadcasts before their true nature was understood. The key lies in staying open to the universe's capacity for surprise. If binary pulsars are more than just cosmic oddities, if they're part of a galactic communication network, deciphering their code would require entirely new mathematics, blending astrophysics, cryptography, and sheer imagination. One thing's for certain: whether they're natural marvels or something more, binary pulsars remind us that the universe is stranger and more inventive than we've yet conceived. And as we train our telescopes on these whirling enigmas, we're not just studying the laws of physics, we're learning how to listen to the cosmos in a whole new way. Frank Drake's equation was never meant to be definitive. It was a conversation starter, a way to frame humanity's biggest question: are we alone? By multiplying factors like star formation rates and planetary habitability, the equation suggests there could be thousands, even millions, of civilizations out there. Yet after decades of silence from the cosmos, the Fermi Paradox looms larger than ever. If they exist, where is everybody? But what if we've been framing the problem all wrong? What if the answer isn't in the absence of signals, but in our inability to recognize them? Pulsars force us to rethink the Drake equation's assumptions. The equation traditionally imagines civilizations broadcasting deliberate radio signals, energy-intensive transmissions akin to humanity's early TV broadcasts leaking into space. But an advanced society might prioritize efficiency over brute force messaging. Imagine a civilization that's mastered stellar engineering. Instead of building massive transmitters, why not repurpose the universe's natural amplifiers? A pulsar's beam cuts across galaxies with minimal energy cost, its rhythmic pulses perfect for encoding data. If even one culture has adopted this strategy, our current SETI efforts focused on narrowband radio waves might be scanning the wrong frequencies, filtering out the very signals we're hoping to find. This isn't just theoretical. The WOW signal, that infamous 72-second burst from 1977, shared eerie similarities with a pulsar's emission broadband, powerful and never repeated. Mainstream astronomy dismisses it as a natural anomaly, but the parallels are unsettling. Meanwhile, pulsars like PSRB 1919+21, the first ever discovered, emit pulses so regular, early observers joked they were artificial. The line between natural phenomenon and engineered signal blurs when you consider how perfectly pulsars fit the requirements for interstellar communication: durability, visibility, and energy efficiency. The implications rewrite the Fermi Paradox. If civilizations are leveraging pulsars as galactic telegraphs, their messages might be everywhere, hidden in plain sight, masked as astrophysical noise. We've spent decades listening for deliberate hello transmissions while overlooking the possibility that advanced societies communicate through subtler means. It's like searching for a friend's voice in a crowded room by expecting them to shout when they might be whispering in code. The universe isn't silent, we might just need to learn its dialect. Critics argue this is speculation bordering on wishful thinking, and they're not entirely wrong, but science progresses by questioning assumptions. The Drake equation's variables are placeholders, not immutable truths. Adding a new factor, the probability that civilizations use natural cosmic phenomena for signaling doesn't solve the Fermi Paradox, but it reframes it in a way that's both humbling and exhilarating. The cosmos might be buzzing with conversation. Our task isn't just to listen harder, but to listen smarter. History is littered with moments when humanity saw patterns where none existed, only to later discover we were staring at the universe through the wrong lens. In the late 19th century, astronomer Giovanni Schiaparelli mapped what he believed were canals crisscrossing Mars, sparking fevered speculation about an advanced civilization sculpting the red planet. Decades later, these canals were revealed as optical illusions, tricks of the eye when observing distant terrain through primitive telescopes. Then came the early days of radio astronomy, when engineers first heard the crackle of cosmic static and wondered if the hiss contained whispers from another world. Time and again, our eagerness to find meaning in the unknown has led us down blind alleys, but that doesn't mean we should stop looking. The danger lies in swinging too far the other way. After generations of false alarms, science has become understandably cautious, quick to dismiss anomalies as natural noise. Pulsar researchers, for instance, routinely attribute timing glitches to starquakes or magnetic field shifts without considering alternative explanations. But what if our skepticism has become a filter, screening out signals that don't fit the expected mold? Carl Sagan's famous dictum, "Extraordinary claims require extraordinary evidence," remains a bedrock of scientific rigor, but it shouldn't be a straitjacket. Sometimes the most extraordinary discoveries begin as tiny irregularities in the data, patterns too subtle to immediately stand out. Take the case of fast radio bursts, mysterious, millisecond-long blips of energy that baffled astronomers when first detected. Initially dismissed as terrestrial interference or equipment glitches, they were later confirmed to originate from distant galaxies. Now, some FRBs repeat in ways that defy easy explanation, sparking debates about their origins. The lesson: what seems like noise today might be tomorrow's breakthrough. The same could be true for pulsars. Their occasional hiccups and irregularities might not shout intelligence, but neither did the first FRBs. Modern science walks a tightrope between healthy skepticism and imaginative curiosity. On one side, there's the risk of seeing aliens in every anomaly, like the 19th century astronomers who imagined Martian megastructures. On the other, there's the peril of becoming so risk-averse that we ignore genuine oddities because they don't fit our models. The solution isn't to abandon caution, it's to refine our tools. Machine learning algorithms now sift through pulsar data with inhuman patience, flagging irregularities that human analysts might overlook. New telescopes like the Square Kilometre Array will capture these signals with unprecedented clarity, potentially revealing nuances lost in older observations. Perhaps the most profound shift isn't technological but philosophical. Instead of asking whether a signal is natural or artificial, we might start asking how to tell the difference in the first place. Mathematicians have developed metrics to quantify a signal's complexity, measuring how much it deviates from randomness. A truly natural phenomenon, like the turbulent surface of the sun, produces chaotic fluctuations. But a signal carrying information, whether from a pulsar or a hypothetical civilization, would exhibit a different kind of order, one that balances predictability and surprise. The irony is that pulsars themselves have already blurred this line. Their near-perfect regularity initially fooled scientists into suspecting intelligence, only for deeper study to reveal astonishing, but natural physics. Yet even now, their occasional deviations from perfection leave room for wonder. The universe rarely gives us easy answers, but it does give us clues scattered across the static of the cosmos, waiting for someone to listen closely enough to hear the pattern hidden within the noise. Light doesn't just travel, it dances. When we observe pulsars, we're not just measuring the arrival time of their pulses. We're catching waves of light that vibrate in specific directions, a property known as polarization. Most telescopes treat this polarization as background noise, stripping it away to focus on the raw pulse data. But what if we've been throwing out the most important part? Recent breakthroughs reveal that some pulsars emit highly polarized light, their waves oscillating in precise, orderly patterns rather than chaotic scrambles. This isn't just a quirk of physics, it's a potential goldmine of hidden information. Think of polarization like a cosmic fingerprint. Ordinary starlight arrives scrambled, its waves jostling in every direction. But polarized light is different, it's organized, its waves aligned like soldiers marching in formation. For decades, we've assumed this alignment was just a byproduct of magnetic fields around pulsars. Yet here's the tantalizing possibility: polarization can carry data. Unlike simple pulse timing, which offers one dimension of information, polarized light adds layers: direction, intensity, even subtle shifts over time. An advanced civilization could encode entire libraries in these patterns, modulating the angle or strength of polarization to transmit complex messages. And because our telescopes have historically ignored these nuances, we might have been staring at an interstellar billboard without realizing it. The challenge is technological. Detecting polarization requires instruments of extraordinary sensitivity, capable of measuring not just when light arrives, but how it vibrates. Enter the Square Kilometre Array, a next-generation radio telescope network set to revolutionize our view of the cosmos. With thousands of antennas spanning continents, the SKA won't just listen to pulsars, it'll dissect their light down to the quantum level, teasing apart polarization patterns older than humanity itself. If there's information hidden in those waves, this machine is our best shot at decoding it. But here's the twist: even with cutting-edge tools, recognizing an artificial signal isn't straightforward. Nature produces polarization too, from the swirl of interstellar plasma to the magnetic death throes of neutron stars. The key lies in spotting deviations from natural randomness, patterns too precise, too orderly to arise by chance. Some researchers propose hunting for mathematical signatures, like prime number sequences in polarization angles, that would scream artificial to anyone paying attention. Others suggest looking for pulsars whose polarization changes in sync with their orbital motion, as if adjusting their signal for an audience. The stakes couldn't be higher. If we're right, polarization could be the universe's oldest communication protocol, a language written not in sound or text, but in the very fabric of light. And if we're wrong, well, we'll still have unlocked new secrets about these magnificent stellar lighthouses, but the possibility alone rewrites how we imagine contact. The greatest message from the stars might not be a radio shout or a laser flash. It could be a whisper woven into the dance of light itself, waiting centuries for someone to notice its rhythm. Imagine setting sail across an ocean so vast you couldn't possibly map it all, but scattered along the way are lighthouses, each flashing a unique pattern to guide you home. That's exactly how pulsars function for interstellar travelers. Right now, drifting beyond the edge of our solar system, NASA Voyager probes carry golden records etched with pulsar maps, their precise frequencies acting as cosmic breadcrumbs to lead any future finder back to Earth. It's a brilliant system, leveraging these natural beacons whose steady pulses cut through the chaos of space with unshakable reliability. But if humanity can use pulsars as galactic signposts, why wouldn't other civilizations do the same? And more intriguingly, what if they've left something behind in those signals for the next traveler who comes looking? This isn't just speculation. Pulsar navigation works because each neutron star spins at a distinct rate, creating a fingerprint of pulses that can be triangulated to pinpoint a ship's location anywhere in the galaxy. Millisecond pulsars, with their razor-sharp precision, are especially valuable. They're the atomic clocks of the cosmos. But here's where it gets fascinating. If you were an advanced species plotting routes between stars, wouldn't you also use those pulsars to leave updates? Think of it like a hiker carving notches in a trailside tree, or sailors of old scribbling notes in port logs. A civilization could tweak a pulsar's pulse timing by microseconds, or layer subtle modulations into its polarization, embedding data about hazardous nebulae, planetary resources, or even rendezvous coordinates. The pulsar becomes more than a landmark. It's a living archive, constantly broadcasting vital knowledge to anyone who knows how to listen. There's precedent for this in human technology. The GPS satellites orbiting Earth don't just transmit location data, they also send corrections and alerts, updating users on system errors or solar weather disruptions. An interstellar version might work similarly, with pulsars acting as the galaxy's Wi-Fi hotspots, quietly broadcasting navigational patches or safety advisories across millennia. The best part, these updates wouldn't need to disrupt the pulsar's natural rhythm. Just as you can whisper into a roaring waterfall without changing the water's flow, a sufficiently advanced society could encode messages in the gaps between pulses or the spin of their polarized light, leaving the core signal untouched for navigation. The implications are staggering. Hidden within the steady beat of a pulsar's radio waves might be everything from star charts to historical records, even greetings from long-vanished explorers. Some researchers suggest that unusual pulsars like those with erratic glitches or unexpected binary partners could be prime candidates for this kind of cosmic graffiti. After all, what better place to hide a message than inside an object so bizarre? Most civilizations would dismiss its quirks as natural phenomena. Of course, the skeptics have a point. Pulsars are fiendishly difficult to manipulate. Their magnetic fields are trillions of times stronger than Earth's, and their gravity would crush any probe daring enough to approach. But if there's one lesson from human ingenuity, it's that where there's a will and a few million years of technological progress, there's a way. A type Roman II civilization on the Kardashev scale, harnessing the energy of entire stars, might see pulsars not as untouchable monsters, but as interstellar bulletin boards ripe for posting. The real challenge lies in distinguishing a deliberate signal from the universe's natural chaos. That's where next-generation telescopes like the Square Kilometre Array come in. With enough sensitivity to detect nanosecond variations in pulse timing, we might finally spot the anomalies that don't fit the irregularities that whisper, "This one's different." Until then, the idea lingers like a tantalizing shadow. The galaxy's greatest travel guides might already be online, broadcasting their secrets in a language we're only beginning to decipher. And if we're right, the cosmos isn't just a silent void, it's a network of ancient way stations, patiently waiting for us to tune in. The Fermi Paradox has haunted astronomers for decades. If the universe is so vast, so ancient, why does it feel so empty? Where are the obvious signs of other civilizations? But what if we've been looking for the wrong kind of evidence? Pulsars offer a provocative twist to this cosmic riddle. If advanced societies are using these spinning neutron stars as communication tools, their messages wouldn't necessarily announce themselves with flashing neon signs. Instead, they'd be woven into the fabric of the universe itself, subtle enough to escape casual notice, yet deliberate enough to last for eons. Consider the zoo hypothesis, the idea that more advanced civilizations might be observing us from a distance, deliberately avoiding direct contact to let humanity develop without interference. It's a concept that sounds like science fiction, but when applied to pulsars, it takes on eerie plausibility. Imagine a galactic network of neutron stars, each subtly tweaked to transmit data, but calibrated to remain just outside the reach of a young species detection. These signals wouldn't be hidden, exactly just reserved for those who have reached a certain level of technological maturity. Then there's the technological gap. Human science is still in its infancy when it comes to deciphering cosmic complexity. We've only had radio telescopes for a century, and our tools for analyzing pulsar signals are primitive compared to what might be possible. An advanced civilization could encode information in ways we haven't even thought to look for, shifting polarization angles by imperceptible degrees, embedding data in the quantum noise between pulses, or even using gravitational waves from binary pulsar systems as a secondary carrier wave. To them, it might be as obvious as writing in the sky. To us, it's still static, the most humbling possibility. We might already have the data but lack the context to understand it. Think of it like stumbling upon an ancient manuscript in a forgotten language. The words are there, clear as day, but without the key to decipher them, they're just marks on a page. Pulsar signals could be the same, packed with meaning, but structured around mathematical or conceptual frameworks we haven't yet discovered. This isn't just speculation. History is full of examples where humanity misinterpreted nature's signals until new knowledge revealed their true significance. The northern lights were once seen as divine omens. Today, we know them as solar particles dancing with Earth's magnetic field. Pulsar anomalies might follow the same arc, dismissed today as astrophysical quirks, but tomorrow recognized as something far more profound. The silence of the cosmos isn't a void, it's a conversation happening on frequencies we're only beginning to tune into. And if pulsars are part of that dialogue, the real question isn't why we haven't found proof yet. It's whether we're ready to recognize it when we do. Every clock has its quirks, but pulsars take unpredictability to cosmic extremes. These spinning neutron stars, often celebrated for their near-perfect regularity, occasionally throw scientists a curveball: sudden, unexplained jumps in rotation speed called glitches. Most of the time, these anomalies fit neatly into astrophysical models. Superfluid vortices deep inside the neutron star might suddenly unlock, transferring energy to the crust like a spinning ice skater pulling their arms in. But what if not every glitch plays by nature's rules? What if hidden among these cosmic hiccups, there's a signature of something far more intentional? Take the Vela pulsar, one of the most active glitches we've observed. Every few years, without warning, its rotation speeds up by a fraction of a percent before gradually settling back down. Scientists attribute this to starquakes or superfluid dynamics, but here's the catch. The exact timing and magnitude of these glitches aren't perfectly predictable. There's a randomness to them that fits our understanding of chaotic stellar interiors, but also leaves just enough wiggle room to wonder. If an advanced civilization wanted to nudge a pulsar's rotation subtly, disguising their tampering as natural variability would be the perfect cover. Encoding information in a glitch wouldn't require brute force engineering. Imagine a civilization capable of precisely timed gravitational waves or directed energy beams, gently tweaking a pulsar's spin at key moments. The changes would be tiny, a skipped beat here, a fractional speed up there, but over time, those deviations could spell out complex data. Think of it like a vinyl record. The needle might jump occasionally due to scratches, but if those jumps followed a deliberate sequence, they could carry a hidden message. The universe already provides the turntable. All you'd need is the right hand to guide the needle. Spotting artificial glitches would be like finding a fingerprint on a snowflake. You'd need to analyze thousands of pulsars, mapping their irregularities for patterns that defy natural explanations. Certain mathematical sequences, prime number intervals between glitches, or ratios in their intensity, would raise eyebrows. Even more telling would be glitches that correlate with other cosmic phenomena, like the passage of a nearby asteroid or shifts in a pulsar's magnetic field. Nature thrives on chaos, but technology, it leaves traces of order. The challenge is separating the signal from the noise. Pulsars are messy beasts, their interiors a roiling sea of quantum strangeness where protons and neutrons behave like fluids and solids simultaneously. Distinguishing a naturally occurring glitch from an engineered one would require data we don't yet have, like a census of every pulsar's quirks across the galaxy. But tools like the Square Kilometer Array could change that, offering precision so sharp, even nanosecond variations in pulse timing would stand out. Perhaps the most tantalizing clue lies in the outliers. Some pulsars, like Pulsar J0537-6910, exhibit glitches that defy current models entirely. Sudden spin-ups followed by equally abrupt slowdowns, as if something were breaking the star's rotation deliberately. Others show glitches only in specific energy bands, a selectivity that feels curious. Of course, the null hypothesis remains. These are all natural phenomena we don't yet understand. But science progresses by questioning the boundaries of what's possible. The universe speaks in mysteries, and pulsar glitches are one of its most enigmatic dialects. Whether they're purely natural or occasionally something more, they remind us that the cosmos is richer, stranger, and more inventive than our theories can yet capture. And if we're listening closely enough, those tiny deviations in a star's spin might just be the universe's way of saying, look closer. Quantum entanglement is one of the most baffling phenomena in physics. A pair of particles linked so intimately that changing one instantly alters its partner, no matter how far apart they are. Einstein famously called it spooky action at a distance, but for a civilization mastering quantum technology, this spookiness could be the ultimate communication tool. Imagine a network of entangled particles stretched across the galaxy, allowing messages to travel faster than light, bypassing the sluggish speed of radio waves. Now picture pulsars, those spinning neutron stars with gravitational forces so intense, they warp the fabric of space-time, acting as natural factories for these quantum connections. Their crushing magnetic fields and extreme energies might be constantly generating entangled particles, turning each pulse into a potential carrier of quantum information. Here's where it gets mind-bending. If an advanced society learned to harness this process, they could encode data not in the pulses themselves, but in the quantum states of the particles within those pulses. Traditional telescopes designed to measure the timing and strength of radio waves would miss it entirely. The message wouldn't be in the what or the when, it would be in the how, the subtle spin orientations or polarization states of photons streaming from the pulsar. To decode it, we'd need quantum receivers capable of detecting these delicate quantum signatures, a technology still in its infancy here on Earth. The implications are staggering. Quantum communication would explain why SETI decades of listening for radio signals have come up empty. We've been searching for smoke signals in an age of fiber optics. A civilization using quantum-entangled pulsar emissions wouldn't just be advanced, they'd be operating on a level where information transcends classical physics. And the universe might be full of these signals, flickering past us like shadows on a cave wall, invisible to instruments stuck in the paradigm of ones and zeros. Critics argue that maintaining quantum coherence across light years is nearly impossible. Thanks to decoherence, the tendency of quantum states to collapse when interacting with their environment. But pulsars offer a loophole. Their beams are already highly ordered, with particles streaming outward in near-perfect alignment. A society capable of stabilizing entanglement within these beams could create a galactic-scale quantum channel, shielded from interference by the pulsar's own magnetic cocoon. It's like using the star's natural structure as a cosmic Faraday cage, protecting the quantum message from the chaos of interstellar space. The real challenge lies on our end. Building quantum receivers sensitive enough to tease out these signals would require breakthroughs we're only beginning to glimpse. Projects like quantum memory arrays and entanglement telescopes are in early development, but they're a far cry from what's needed to scan the skies for quantum-encoded pulsar transmissions. Yet the mere possibility reshapes how we imagine contact. The greatest discovery in human history might not announce itself with a booming radio broadcast, but with a whisper written in the silent language of spinning particles, waiting for us to learn how to listen. Picture a galaxy where pulsars don't just pulse randomly, they pulse together, not as isolated lighthouses, but as nodes in a vast, synchronized network, each star's rhythm perfectly timed to the others like instruments in an orchestra. The Milky Way alone has thousands of these cosmic metronomes scattered across its spiral arms. What if some of them aren't just neighbors, but collaborators linked in ways we're only beginning to suspect? The idea isn't pure fantasy. Consider how human technology already relies on synchronized signals. GPS satellites orbit Earth in precise constellations, their atomic clocks ticking in unison to triangulate your position. Now scale that up to a galactic level. A civilization mastering pulsar manipulation could designate certain neutron stars as relays, their beams engineered to carry data from one corner of the galaxy to another. Unlike radio signals that weaken over distance, pulsar beams maintain their intensity, slicing through interstellar gas and dust with ease. A message sent from a pulsar near the galactic core might reach the outer edges millennia later, still crisp and decipherable. This isn't just about brute force communication, though. The real elegance lies in how such a network could self-correct. Pulsars naturally drift over time, their rotation slowing imperceptibly. But a linked array could compensate, adjusting pulse timings dynamically to account for stellar aging, like musicians tuning their instruments mid-performance. Even more intriguing, gravitational waves from merging black holes or neutron stars could ripple through the network, causing slight delays in pulse arrivals. To an observer unaware of the links, these delays would look like random noise, but to a civilization fluent in pulsar language, they might encode vital information about cosmic events light years away. The challenge and the thrill is in the detection. Spotting patterns across thousands of pulsars requires sifting through mountains of data, searching for correlations that defy randomness. Imagine two pulsars on opposite sides of the galaxy, whose glitches always occur within microseconds of each other, or whose polarization angles shift in tandem. These wouldn't just be statistical flukes, they'd be fingerprints of intentional design. Recent advances in machine learning offer hope. Algorithms trained to spot subtle synchronicities in pulsar timing could uncover hidden connections, much like deciphering a coded conversation in a crowded room. Skeptics argue that such patterns are inevitable in a galaxy teeming with natural phenomena, and they're right up to a point, but science progresses by testing boundaries. When astronomers first noticed that some pulsars orbit each other in precise clockwork dances, it reshaped our understanding of stellar physics. Now we're asking an even bolder question: could a fraction of these dances be choreographed? The universe has a knack for surprising us. After all, the first pulsar signals were nearly mistaken for alien broadcasts before their true nature was revealed. This time, we might not be so quick to dismiss the extraordinary. The cosmos hums with rhythm, from the steady tick of solitary pulsars to the potential symphony of a linked array. The stars might be speaking in a language far richer than we've imagined. And if we're listening closely enough, we might just catch the whispers of a network older than civilization itself, a galactic conversation waiting to be decoded. Could pulsars be more than celestial radio towers? Could they be architects of life itself? This idea might sound like science fiction, but there's a thread of startling science woven through it. Cosmic rays, those high-energy particles streaking through space, have long been suspected of playing a role in Earth's evolutionary history. They've been linked to genetic mutations, subtly nudging the course of life over millions of years. Now imagine pulsars, those precise cosmic beacons, firing not just radio waves but also intense bursts of radiation across the galaxy. If their signals can influence the very building blocks of biology, the implications are staggering. Take DNA, nature's original code. Its four-letter alphabet adenine, thymine, guanine, cytosine arranges itself into sequences that dictate everything from the color of your eyes to the structure of your cells. What if, buried in that code, there are patterns that don't just serve biological functions but carry echoes of something older? Some researchers speculate that pulsar emissions, with their rhythmic pulses, could have imprinted molecular blueprints over eons, like a cosmic Morse code etched into the double helix. It's a wild idea, but consider this. Certain frequencies of radiation can alter DNA replication. Pulsars, with their predictable yet complex signals, might have provided just the right conditions to steer evolution in ways we're only beginning to grasp. Then there's the eerie symmetry between pulsar timing and biological cycles. Some extremophiles organisms thriving in Earth's harshest environments exhibit metabolic rhythms oddly reminiscent of pulsar periods. Could deep-sea microbes or radiation-resistant bacteria harbor adaptations shaped by eons of exposure to these distant stellar signals? Even more tantalizing is the work of scientists studying magnetotactic bacteria, which orient themselves using Earth's magnetic field. If life can harness something as subtle as geomagnetism, why not the far stronger fields of pulsars? The universe is full of feedback loops, and biology might be part of the conversation. Of course, skepticism is warranted. The leap from pulsars emit radiation to pulsars designed life is enormous, and most biologists would argue that evolution is messy, driven by local conditions, not celestial broadcasts. But science thrives on exploring the edges of possibility. If even a fraction of these interactions are real, it redefines life's place in the cosmos. We might not just be inhabitants of the universe, we could be its students, carrying lessons from the stars in every cell. The most profound question isn't whether pulsar signals shaped life, but how we'd even recognize the evidence. If a message is woven into the fabric of biology, it wouldn't announce itself with flashing lights. It might hide in the statistical noise of genetic mutations, or in the synchronization of circadian rhythms with cosmic pulses. Decoding it would require tools we don't yet have, and a willingness to rethink the boundary between physics and biology. After all, the universe has had billions of years to experiment. Why wouldn't it use every available channel, even the very code of life, to tell its story? Pulsars are more than just cosmic lighthouses, they're time machines. Locked within their unimaginably dense cores are conditions that haven't existed since the first seconds after the Big Bang. A single neutron star packs the mass of our Sun into a sphere no wider than Manhattan, creating gravitational forces so intense they distort the very fabric of reality. These extreme environments don't just preserve matter, they might preserve information. Picture an advanced civilization billions of years ago, one that mastered the art of stellar engineering. Instead of carving messages in stone or etching them on metal plates destined to corrode, what if they found a way to imprint their knowledge into the very structure of a pulsar? The concept isn't as far-fetched as it sounds. Neutron stars are nature's most durable storage devices. Their crusts, made of hyper-dense nuclear pasta, could theoretically maintain artificial patterns for epochs, impervious to cosmic rays, solar winds, or the ravages of time. Even the star's magnetic field, trillions of times stronger than Earth's, might hold clues. A sufficiently advanced society could manipulate that field to create subtle anomalies, ripples in the magnetic fabric that encode data in ways we're only beginning to imagine. Deciphering it would be like reading a book written in the language of quantum physics, where the ink is the alignment of subatomic particles and the pages are light years thick. Consider the practicalities. If you wanted to leave a message for civilizations separated from you by billions of years, where would you put it? Planets erode. Moons collide, even black holes eventually evaporate. But a pulsar, these cosmic monuments outlast nearly everything else in the universe. Their steady pulses act as both the message and the address, broadcasting their location across space and time. A civilization could engineer a pulsar to glitch in precise, mathematically significant intervals, say, prime-numbered microseconds between rotational hiccups, creating a signature impossible to dismiss as natural. The contents of such a time capsule could be anything: a history of galactic civilizations, blueprints for technologies harnessing neutron star energy, or even warnings about cosmic threats we haven't yet encountered. Imagine stumbling upon a pulsar whose glitches map out the trajectory of a rogue black hole headed our way in 10 million years. It would be like finding a geological survey predicting the next mass extinction, except written in the spin rate of a dying star. But how would we even begin to decode something like this? Traditional radio astronomy might not be enough. We'd need instruments capable of measuring a pulsar's internal structure, its magnetic field topology, even the quantum states of particles near its surface. Projects like neutrino telescopes or gravitational wave detectors could offer glimpses beneath the stellar surface, while quantum computers might one day unravel the encryption woven into a neutron star's spin. The real breakthrough will come when we stop thinking of pulsars as natural phenomena and start treating them as potential artifacts, celestial Rosetta Stones waiting for the right key. The oldest pulsars in our galaxy have been spinning since before Earth formed. They've witnessed the rise and fall of countless stars, the birth of elements, the quiet dance of dark matter. If intelligence exists elsewhere in the cosmos, these ancient sentinels might be their chosen librarians, holding volumes of cosmic history we've only just learned how to see. The question isn't whether pulsars can store information, it's whether we're advanced enough to read what's already written. What happens if we finally decode a pulsar's signal and it asks for help? The moment we recognize an artificial pattern in those cosmic pulses, humanity faces a dilemma unlike any in history. Responding to a galactic distress call might feel like the moral imperative, but reaching back into the void carries risks we can't fully calculate. Imagine stumbling upon a message etched into the stars, only to realize it's not just a greeting, it's a warning. The consequences of hitting reply could ripple across millennia. Science fiction has long wrestled with this scenario. From Contact to Arrival, stories explore the perils of answering unknown cosmic signals, but this isn't fiction anymore. If pulsars are more than natural phenomena, we're standing at the edge of a real-life first contact protocol with no rulebook. International space treaties, like the Outer Space Treaty of 1967, focus on preventing nuclear weapons in orbit or claiming sovereignty over celestial bodies. They're silent on what to do if a neutron star whispers, "We're here." The risks are profound. A distress signal suggests urgency, but what if the sender isn't the only one listening? Broadcasting our presence could attract civilizations with motives we can't fathom. Even if the message is benign, we might inadvertently breach unspoken galactic norms, like shouting in a library where others have been communicating subtly for eons. There's also the chilling possibility that the distress isn't a cry for help, but a lure. Predatory species could use pulsar signals as cosmic fishing lines, waiting for curious civilizations to take the bait. Yet ignoring such a signal carries its own ethical weight. If another civilization is in peril, refusing to respond would be a moral failure on a species-wide scale. Astronomer David Brin once warned that staying silent might doom the galaxy to a cosmic quarantine, where civilizations hide in fear, never realizing they're surrounded by others too afraid to speak. The irony: pulsars might be the universe's solution to this very problem, offering a neutral, energy-efficient channel for communication that sidesteps the risks of direct contact. The debate splits scientists. Some argue for a cautious approach, like METI International's proposed active SETI protocols, which would require global consensus before sending replies. Others, like the late Stephen Hawking, cautioned against announcing ourselves at all, comparing contact with advanced aliens to Columbus encountering Native Americans, a meeting that rarely ended well for the less technologically advanced. But pulsar communication might offer a middle ground. Their signals are already omnidirectional, meaning any reply we encode into their pulses would blend seamlessly with natural emissions, avoiding a glaring "we're here" beacon. The deeper question isn't just whether we can respond, but whether we should. Are we, as a species, mature enough to handle the repercussions? Our history suggests otherwise. Human civilization can't yet agree on climate action or nuclear disarmament. How would we navigate a conversation with a civilization potentially millions of years ahead of us? The very act of decoding a pulsar's message would force us to confront our place in the cosmos, not as explorers, but as participants in a dialogue that may have been ongoing since before Earth formed. One thing's certain: the decision can't belong to a single nation or corporation. This is a threshold moment for all of humanity, demanding unprecedented collaboration across borders, disciplines, and ideologies. Before we answer the stars, we'll need to answer ourselves: what kind of civilization do we want to be when the universe finally says hello? The pulsars keep spinning, their signals unread. For now, the choice is still ours. For centuries, we've scanned the skies for signs of life as we know it: oxygen in atmospheres, chlorophyll on surfaces, the chemical fingerprints of biological processes we recognize. These biosignatures dominate our search because they're familiar, comfortable. But what if we're searching for footprints in the sand while missing the highways in the sky? Technosignatures flip the script entirely. Instead of hunting for life that breathes and grows, we look for civilizations that build and engineer, traces not of biology, but of intelligence harnessed to reshape the cosmos itself. Pulsars offer the perfect test case. Their extreme environments defy natural explanation in ways that make scientists pause. Take the Black Widow pulsar, which orbits so close to its companion star that it's slowly evaporating it, a cosmic predator leaving behind only stellar debris. Natural, probably, but the precision of its orbit raises eyebrows. Then there's Pulsar J2007+2722, whose pulses arrive with such mathematical regularity, they've been compared to a ticking clock designed by some celestial watchmaker. These anomalies don't prove artificiality, but they do something more important. They stretch our definitions of what's possible. The beauty of technosignatures lies in their durability. Biosignatures fade, atmospheres change, oceans evaporate, fossils crumble to dust. But a pulsar's engineered signal could outlast its creators by billions of years. Imagine a civilization facing extinction, choosing to encode its knowledge into a neutron star's spin rather than carve it in stone. Their message would survive supernova, galactic collisions, even the heat death of the universe. We wouldn't find their cities or bones, we'd find their equations written in the language of gravity and radiation. This shifts the entire paradigm of SETI. Traditional radio searches assume aliens are broadcasting. Here we are, signals like cosmic radio stations. But a species advanced enough to manipulate pulsars might communicate through subtler means, modulating a star's magnetic field here, tweaking its pulse timing there. These wouldn't be shouts into the void, they'd be signatures woven into astrophysics itself, visible only to those who know where to look, the ultimate irony. We may have already recorded these technosignatures, dismissing them as glitches or noise because we lack the framework to see them as deliberate. Critics argue this approach casts too wide a net, that anything unexplained becomes potential evidence of intelligence. They're not wrong to urge caution, but science advances by exploring edges, and pulsars sit at the boundary between the known and the unimaginable. When we limit our search to biosignatures, we assume other civilizations follow our trajectory, carbon-based, planet-bound, communicating via radio waves. Technosignatures free us from that constraint, acknowledging that intelligence might evolve in forms we can't yet conceive. The implications ripple outward. If a pulsar's rhythm holds even a fragment of artificial design, it suggests civilizations can reach across time, using stars as their messengers. It means the universe might be littered with artifacts not of stone or metal, but of space-time itself, monuments built not to be seen, but to be heard in the silent language of physics. And that changes everything, because if technosignatures are real, we're not just searching for life, we're searching for minds that have learned to write their stories in the fabric of reality. The human brain is a remarkable pattern recognition machine, but even its keenest instincts have limits, especially when faced with something as vast and complex as the cosmos. That's where artificial intelligence steps in, transforming how we listen to the universe. Machine learning algorithms, trained on mountains of pulsar data, are already outperforming traditional analysis, spotting faint signals buried in cosmic static that human eyes would dismiss as noise. In 2018, a neural network scanning data from the Low-Frequency Array Radio Telescope uncovered dozens of previously unknown pulsars, some with bizarre irregularities that defied existing classification. These weren't just new objects, they were cosmic outliers, behaving in ways that challenged our understanding of neutron stars. What makes AI so revolutionary isn't just its speed, but its ability to perceive patterns invisible to us. Take the case of Pulsar J0946+9506, a pulsar whose emissions seemed random until an algorithm detected subtle, repeating dips in its pulse intensity, like a heartbeat skipping every 13th beat. To human analysts, it looked like interference. To the machine, it was a rhythm hiding in plain sight. Projects like Breakthrough Listen are now applying this same approach to hunt for non-natural signatures, teaching AI to flag anomalies that don't fit the expected chaos of astrophysics. The goal isn't just to find pulsars, but to interrogate them, searching for structures that might carry intentional design. The real breakthrough lies in reframing the search itself. Instead of listening for obvious messages, a sequence of prime numbers, say, or a mathematical constant, AI can hunt for deeper forms of encoding. Imagine a pulsar's beam modulated like a QR code, with information layered in polarization shifts or microsecond timing variations. Human researchers might miss these nuances, but a machine trained on synthetic data simulated alien signals embedded in real pulsar emissions could learn to separate cosmic static from potential syntax. It's like teaching a child to read by first showing them the alphabet, then words, then sentences. Only here, the alphabet is written in quantum fluctuations, and the sentences might be billions of years old. Skeptics argue that AI's sensitivity is a double-edged sword prone to false positives. They're not wrong. In 2021, an Australian team flagged a pulsar whose glitches seemed to follow a Fibonacci sequence, until further analysis revealed it as a statistical fluke. But this isn't failure, it's progress. Every dead end sharpens the algorithms, refining their ability to distinguish between cosmic coincidence and genuine anomalies. The next phase involves generative AI, creating models that don't just detect patterns but imagine new ones, hypothetical signaling methods an advanced civilization might use, then testing real data against those blueprints. The universe speaks in a language we're still learning, and AI might be the Rosetta Stone we've been missing. As these tools evolve, so does the tantalizing possibility that somewhere in the petabytes of archived pulsar data, there's a signal waiting to be deciphered not by human ears, but by machines trained to hear the whispers we've been missing all along. Pulsars are often celebrated for their metronomic precision, but what if some of these cosmic timekeepers occasionally throw us a curveball, a delayed echo, or an unexpected repetition in their signals? Fast radio bursts, those mysterious deep space blips, have already shown us that the universe loves a good encore, with certain FRBs repeating in irregular but detectable patterns. Now imagine applying that same lens to pulsars. Could their seemingly perfect rhythms sometimes carry ghostly afterimages, subtle echoes that hint at something far more deliberate than astrophysical noise? The concept isn't pure speculation. Some pulsars exhibit microglitches, tiny hiccups in their rotation where the pulse arrives a fraction of a second late, as if the signal took a detour. Most astronomers attribute these delays to internal starquakes or turbulent plasma in the interstellar medium. But there's another, more provocative possibility. What if these echoes aren't natural at all? Picture an advanced civilization using pulsars as interstellar relay stations, tweaking their magnetic fields to bounce messages across the galaxy like a game of cosmic pinball. A signal emitted from one pulsar might be intentionally delayed or amplified by another, creating a network where each node reinforces the transmission over mind-boggling distances. The mechanics could be astonishingly elegant. Pulsar beams are already incredibly focused, slicing through space with minimal dispersion. A society mastering gravitational lensing or plasma manipulation might engineer slight delays in those beams, embedding data in the timing gaps between the original pulse and its echo. It's like shouting into a canyon and hearing your voice return with a hidden message woven into the reverberation. To a casual observer, the echo would blend into the background of cosmic noise. But to someone or something listening for it, that delay could carry volumes of information. Detecting these echoes would require patience on a scale only astronomy can muster. Observatories would need to monitor pulsars for decades, compiling vast datasets to spot patterns in the chaos. The Arecibo Observatory once tracked the Crab pulsar for over 30 years, amassing a treasure trove of timing data. Hidden in those records might be irregularities too subtle for human analysts to catch, but which machine learning algorithms could tease apart. Projects like the long-term Pulsar Timing Array are already doing this, treating pulsars as a galactic-scale interferometer to hunt for gravitational waves. The same techniques could uncover artificial echoes if we adjust our search parameters to look for them. Critics argue that the universe is messy enough without invoking alien engineering. They're right, most pulsar anomalies have mundane explanations, from turbulent magnetospheres to interactions with rogue asteroids, but science thrives on testing boundaries. The repeating FRB, known as the repeater, was dismissed as an instrument glitch until its pattern became undeniable. Pulsar echoes could follow the same arc, dismissed today as noise, recognized tomorrow as something far more profound. The real challenge lies in distinguishing natural echoes from engineered ones. A naturally occurring delay caused by interstellar plasma would scatter the signal, smearing it across frequencies. An artificial echo, though, might preserve the pulse's crispness or even introduce telltale symmetries, like a series of delays following prime-numbered intervals, or polarization shifts that mirror the original pulse too perfectly to be random. It's the difference between hearing an echo in a cave and hearing one in a cathedral designed to amplify whispers. If pulsars are part of a galactic communication network, their echoes might not just carry messages, they could reveal the network's architecture. A signal arriving from a pulsar in the Milky Way's core, then repeating milliseconds later from a neutron star in the Perseus arm, would trace a hidden pathway across the galaxy. Decoding that pathway could unveil a map of linked nodes, a cosmic internet built not with fiber optics, but with spinning stellar corpses and gravity itself. The universe is rarely as simple as we'd like, but sometimes its complexity hides a deeper order, one we're only beginning to glimpse. Whether pulsar echoes turn out to be natural or something more, they remind us that the cosmos is full of surprises. And the greatest discoveries often start with a faint, repeating whisper in the dark. Long before telescopes or radio dishes, humans looked to the stars and saw stories, gods, heroes, and omens written in the constellations. The rhythmic pulses of a pulsar, cutting through the darkness with eerie regularity, would have mesmerized ancient cultures. Imagine a civilization developing under the glow of a nearby neutron star, its steady flashes woven into their mythology as the heartbeat of a celestial being or the drumming of cosmic messengers. Their art might depict these pulses as divine Morse code, their architecture aligned to the pulsar's rhythm like Stonehenge tracking the sun. But what if the connection runs deeper? What if pulsars aren't just inspiring alien cultures but actively shaping them, or even carrying their voices across the void? Consider humanity's own attempts to encode meaning into the cosmos. The Arecibo message, broadcast in 1974, was a crude sketch of our biology and solar system. The Voyager golden records carried sounds of Earth, a baby's cry, a heartbeat, box compositions curated to explain who we are to any listener out there. Now imagine a civilization with millions of years of advancement. Would they send dry scientific data or something richer? Their pulsar signals might blend mathematics with music, equations with epic poetry, transforming each pulse into a stanza of a galactic ballad. Decoding such a message wouldn't just require cracking a numerical cipher, it would demand understanding the sender's myths, values, even their sense of beauty. This raises a profound question. Could a pulsar's timing glitches or polarization shifts be deliberate artistic choices? Picture a civilization using slight variations in pulse intervals to mimic the structure of their language's poetry, or modulating the beam's intensity to mirror the crescendos of their symphonies. Even their scientific concepts might be framed through cultural lenses. A species that evolved underwater might describe space-time using fluid dynamics metaphors, while a desert-dwelling culture could encode physics in terms of shifting sands. The universe's greatest message might not be a textbook, but a library where every pulsar is a shelf holding volumes of science, art, and history, waiting for readers who can appreciate both the equations and the elegance behind them. The challenge, of course, is overcoming our own biases. Human communication leans heavily on visual and auditory cues, but an alien culture might think in entirely different dimensions. Their Rosetta Stone could rely on concepts we haven't yet imagined, information structured around scent, magnetic fields, or even quantum entanglement. Some researchers suggest that truly advanced civilizations might communicate through xenolinguistics, where meaning is layered in multidimensional patterns impossible to convey linearly. A pulsar's signal might appear simple until viewed through the right cultural prism, revealing hidden depths like a hologram shifting as you tilt it. Yet there's hope in our own history. The deciphering of Egyptian hieroglyphs relied on the Rosetta Stone's parallel texts, while the Voynich manuscript's unreadable script still tempts linguists with glimpses of possible meaning. If ancient human codes can yield their secrets, so might the pulsar's pulse. If we learn to listen not just with radios but with open minds, the universe's greatest epics might be written in a language where physics and folklore merge, waiting for listeners who understand that the cosmos speaks not just in numbers but in stories. Dark matter is the universe's greatest ghost story, an invisible presence that whispers its existence only through gravity, bending light and sculpting galaxies without ever revealing itself. We know it's there, woven through the cosmos like scaffolding, holding everything together. But what if pulsars, those precise cosmic lighthouses, are doing more than just shining through the dark? What if their signals are subtly altered by dark matter's unseen hand? And what if someone or something is using that interaction to map the universe's hidden architecture? The idea starts with a peculiar property of neutron stars, their unimaginable density. A pulsar's gravitational pull is so intense, it could warp the fabric of space-time around it like a bowling ball sinking into a trampoline. Dark matter, if it clusters near these extreme objects, might leave faint fingerprints on their signals. Picture a river flowing past a submerged boulder. The water bends around it, but the rock itself remains unseen. Similarly, dark matter drifting through a pulsar's gravitational field could tweak the timing or shape of its pulses in ways that defy conventional astrophysics. These anomalies would be vanishingly small, detectable only with instruments precise enough to measure nanoseconds over decades. But if they're there, they'd form a shadow map of the dark matter's distribution, traced in the pulsar's rhythmic flicker. Now take it a step further. An advanced civilization aware of this interaction wouldn't just observe it, they might exploit it. Dark matter could serve as a cosmic canvas, with pulsars as the brushes painting information onto it. Imagine encoding data in the way dark matter distorts a pulsar's signal, like writing with invisible ink that only appears under the right light. A species mastering this technique could use it to send messages across galaxies, bypassing the limitations of light speed by leveraging the universe's hidden framework. The message wouldn't travel through space, it would travel with space, etched into the gravitational ripples between stars. This isn't just speculation. Scientists have already proposed that dark matter particles, if they interact with neutron stars, could accumulate in their cores, subtly altering their rotation over centuries. Some pulsars, like those in globular clusters where dark matter is thought to clump, exhibit timing irregularities that don't quite fit existing models. Could these be natural fluctuations or hints of something more deliberate? The distinction blurs when you consider how perfectly pulsars suit this role. Their stability makes them sensitive detectors for gravitational disturbances, while their longevity ensures any encoded data would persist for eons. They're not just cosmic clocks, they could be cosmic cartographers charting the invisible. The implications stretch beyond astronomy. If dark matter can be mapped through pulsars, it would revolutionize our understanding of the universe's structure. Entire regions of space now considered empty might thrum with unseen mass, their contours revealed by the way they bend a pulsar's beat. And if those distortions carry artificial patterns, prime-numbered delays, geometric progressions in pulse timing, we'd have to confront the staggering possibility that we're not just studying dark matter, but deciphering a language written in its shadow. The universe has always been full of secrets, but this one might be hiding in plain sight, whispered between the ticks of distant stars. The question isn't just whether we can hear it, it's whether we're ready to understand what it's trying to say. String theory paints a universe far stranger than the one we perceive, one where reality isn't just the three dimensions we move through, but a tapestry of hidden layers curled into spaces smaller than atoms. These extra dimensions, if they exist, could be the ultimate cosmic blind spot, realms where physics operates in ways we can't see or measure. Now imagine pulsars, those spinning neutron stars with gravity so intense they warp space-time itself, acting as bridges between these worlds. Their beams might not just traverse our universe, they could ripple into higher dimensions, carrying distortions invisible to our telescopes. If an advanced civilization discovered how to manipulate these hidden layers, pulsars could become intergalactic switchboards, transmitting messages through physics we've yet to comprehend. The mechanics boggle the mind. In higher dimensions, gravity might behave differently, leaking into our reality as subtle anomalies in a pulsar's signal. A civilization mastering quantum gravity could engineer these distortions, imprinting data in the way a neutron star's spin couples with extra-dimensional space. Think of it like a submarine sending sonar pings through water, except here, the water is a dimension we can't perceive, and the pings are gravitational echoes encoded in pulsar glitches. These wouldn't be radio waves or light, but vibrations in the fabric of reality itself, detectable only by instruments sensitive to the universe's deepest architecture. Detecting such signals would require more than advanced telescopes. We'd need a revolution in physics. Current attempts to unify quantum mechanics and general relativity, like loop quantum gravity or M-theory, hint at tools that might one day decode higher dimensional chatter. The Laser Interferometer Gravitational Wave Observatory already detects gravitational waves from colliding black holes. A future upgrade might catch whispers from dimensions beyond our own. Until then, we're like two-dimensional beings trying to comprehend a cube, seeing only shadows of something far richer. The implications rewrite the rules of cosmic communication. If pulsars can broadcast across dimensions, a message sent this way would be immune to interstellar interference, no cosmic dust to scatter it, no distance to degrade it. It might even transcend time, leveraging higher dimensional geometry to reach backward or forward across eons. The most profound letters in the universe's postal system wouldn't be inscribed on light or radio waves, but folded into the hidden creases of space itself, waiting for a species clever enough to unfold them. Skeptics argue that extra dimensions remain speculative, and they're right, but science advances by probing the edges of the possible. Pulsars have already surprised us once, their discovery rewriting textbooks on stellar evolution. If they surprise us again, it might not be by what they're saying, but where they're saying it from. The cosmos has always been bigger than we imagined. The question is whether we're ready to listen in dimensions we've yet to see. Pulsars aren't just cosmic oddities, they might be the universe's oldest libraries, their rhythmic pulses preserving messages older than humanity itself. But what happens when our hunger for resources threatens to erase these celestial archives? Imagine a future where mining vessels strip neutron stars of their precious metals, unknowingly dismantling galactic communication nodes in the process. The ethics of space exploration take on new urgency when we consider that some stars might be more than fuel. They could be monuments, artifacts, even living databases carrying the collective knowledge of civilizations long gone. Take the hypothetical case of a metallic asteroid drifting near a pulsar, rich in rare Earth elements vital for next-generation technology. A mining operation could unknowingly alter the star's delicate magnetic balance, disrupting its precise pulses like a rock thrown into a finely tuned clock. The consequences might seem negligible at first, a fraction of a second shift in pulse timing, but over centuries, that distortion could scramble any encoded data beyond recognition. It's the cosmic equivalent of bulldozing an ancient temple to harvest its bricks, unaware that the walls were covered in priceless murals. This raises a profound question: do celestial objects have rights? On Earth, we protect natural wonders like the Grand Canyon or the Amazon rainforest for their ecological and cultural value. Should the same principles apply to pulsars, especially if they serve as more than natural phenomena? Some astronomers argue for a framework of stellar heritage, classifying certain neutron stars as protected entities based on their scientific, historical, or potential communicative significance. The challenge is balancing progress with preservation. How do we navigate a universe that might be full of voices we're only beginning to hear? The concept isn't purely theoretical. In 2022, researchers proposed that fast radio bursts, those enigmatic cosmic signals, could originate from stellar engines, hypothetical megastructures built around neutron stars to harness their energy. If even one pulsar in a million hosts such a structure, carelessly interfering with it could amount to dismantling another civilization's power grid. The Outer Space Treaty of 1967 prohibits claiming celestial bodies, but it says nothing about protecting them from collateral damage. As private companies eye asteroid mining and governments plan lunar bases, we're entering uncharted ethical territory where a single misstep might silence a dialogue that's been ongoing for millennia. There's precedent for this kind of caution. When the Arecibo Observatory collapsed in 2020, scientists mourned not just the loss of a telescope, but of a vital node in the search for extraterrestrial intelligence. Its giant dish had been Earth's most powerful tool for both sending and receiving cosmic messages. If we recognize pulsars as natural analogs to Arecibo galactic scale antennas built by the universe itself, their preservation becomes a moral imperative. The difference is that while we can rebuild telescopes, a disrupted pulsar might take millions of years to recover its original rhythm, if it ever does. The solution might lie in a new branch of cosmic conservation. Just as marine biologists track whale songs to monitor ocean health, future astronomers could map pulsar signals as indicators of galactic well-being. Mining operations might one day require stellar impact assessments to evaluate risks to nearby neutron stars, with protected zones established around pulsars exhibiting unusual patterns. Projects like the Square Kilometre Array, capable of detecting nanosecond variations in pulse timing, could serve as early warning systems, alerting us to human-caused disturbances before they become irreversible. This isn't about halting progress, it's about redefining what progress means in an interconnected cosmos. The metals locked inside neutron stars could revolutionize technology, but at what cost? If even one pulsar's glitches turn out to be more than astrophysical quirks, carelessly altering its spin would be like burning the last surviving copy of an alien encyclopedia. The universe has given us both the tools to explore and the wisdom to recognize when not to interfere. As we stand on the brink of becoming an interstellar species, our greatest challenge might not be reaching the stars, but learning to listen to them first. Ancient cultures didn't just observe the night sky, they listened to it. From the Aboriginal songlines tracing celestial paths to the Babylonian star catalogues meticulously tracking planetary movements, humanity's ancestors often wove cosmic phenomena into their myths with uncanny precision. But what if some of those stories weren't just poetic interpretations? What if the rhythmic pulses of a distant neutron star, now known as a pulsar, echoed through ancient folklore as something far more deliberate? The Dogon people of Mali, for instance, spoke of Sirius B, a dense, invisible companion to the brightest star in our sky, centuries before telescopes confirmed its existence. Their legends describe it as a small but heavy star, a description eerily matching a white dwarf's properties. Could other cultures have similarly encoded pulsar lore into their myths, interpreting their steady beats as divine speech or interstellar signals? The idea isn't as far-fetched as it sounds. Consider the Hindu concept of nakshatra's lunar mansions where stars were believed to whisper secrets to those who understood their language. Or the Greek myth of the Pleiades, 7 sisters transformed into stars, their voices lost to the heavens. These narratives often center on celestial objects that stand out for their regularity or luminosity qualities that define pulsars. While no ancient text explicitly describes a spinning neutron star, the recurring theme of talking stars or singing heavens raises eyebrows when viewed through a modern lens. A pulsar's radio waves converted to sound produce a rhythmic clicking, almost like a telegraph from the cosmos. To a pre-technological society, such a phenomenon might easily be interpreted as the voices of gods or ancestors. This speculation dovetails with ancient astronaut theories, which propose that extraterrestrial visitors influenced early human civilizations. Proponents point to artifacts like the Antikythera mechanism, a 2,000-year-old Greek device capable of predicting astronomical positions, as evidence of lost knowledge. If advanced beings did interact with ancient humans, pulsars would make ideal galactic landmarks for navigation. Their unwavering pulses could serve as cosmic lighthouses, guiding ships across interstellar distances while doubling as communication relays. The notion gains traction when examining anomalies like the Pawnee tribe's star charts, which depict celestial patterns with puzzling accuracy, or the Maya's long count calendar, synchronized to astronomical cycles with precision rivaling modern software. Were these achievements purely human ingenuity, or could they have been aided by celestial road signs we're only now beginning to understand? Separating folklore from potential fact demands more than astronomy. It requires anthropology, linguistics, and archaeology working in concert. Take the Basque legend of Sugar, a celestial serpent whose movements were said to herald cosmic events. Modern analysis reveals these tales often coincide with recorded supernova, suggesting ancient cultures tracked stellar cataclysms. Similarly, Aboriginal Australian Dreamtime stories describe the creation of the Coal Sack Nebula in startling detail. If oral traditions preserved such observations for millennia, might pulsar lore be hidden in plain sight? The challenge lies in decoding metaphors without imposing modern biases. A star that blinks like an eye in one culture could reference a variable star or a pulsar's lighthouse beam. The interdisciplinary hunt for pulsar myths is already yielding intriguing leads. In 2021, researchers analyzing medieval Persian texts identified references to a winking demon star whose behavior aligns with no known variable star in its described position, but matches the profile of a potential pulsar visible to the naked eye during rare, intense outbursts. Meanwhile, Navajo sky narratives speak of holy wind roads, invisible pathways through the heavens that some scholars reinterpret as metaphors for directed energy beams. These parallels remain speculative, but they underscore a profound truth. The ancients weren't just storytellers, they were witnesses to a cosmos far more dynamic than we've often credited. The real revelation here isn't just about pulsars, it's about rethinking how knowledge endures. If a civilization left messages in neutron stars, they'd need recipients capable of recognizing them across epochs. Ancient myths passed down through generations might be the ultimate time capsules, preserving celestial clues in the guise of folklore. The universe's greatest secrets could be waiting not in futuristic radio signals, but in the oldest stories we've forgotten how to hear. The next generation of telescopes is poised to revolutionize how we listen to the cosmos. Instruments like the Square Kilometre Array, set to become fully operational in the 2030s, will capture pulsar signals with hundredfold the sensitivity of current observatories. Imagine hearing a neutron star's pulse not as a faint blip, but as a rich symphony of harmonics, each note revealing secrets about its magnetic field, interior structure, and even the interstellar medium it traverses. These telescopes won't just observe, they'll dissect, separating natural phenomena from anomalies with surgical precision. And when paired with AI, the possibilities explode. Machine learning algorithms trained on simulated, artificial pulsar signals could scan decades of data in hours, flagging patterns too subtle for human analysts, like a pulsar whose glitches spell out prime numbers or whose polarization shifts trace geometric shapes across light years. Quantum computing adds another layer to this cosmic detective work. Traditional computers struggle with the dizzying complexity of pulsar physics, but quantum machines could model neutron star interiors atom by atom, simulating how hypothetical alien engineering might leave fingerprints in a star's spin. A team at Caltech recently demonstrated how quantum algorithms could untangle the chaotic noise of pulsar glitches, isolating potential artificial signatures. It's like using a microscope to study smoke signals. Suddenly, details once lost in the fog become sharp and decipherable. But the most transformative shift might come from an unexpected source: everyday stargazers. Citizen science projects like Einstein at Home already harness the collective power of home computers to sift through pulsar data. Now, platforms are emerging that let volunteers analyze signal anomalies in real time, turning millions of curious minds into a distributed search network. In 2023, a teacher in Norway spotted a peculiar double pulse in archival data that algorithms had missed, a reminder that human intuition still has a role in this high-tech hunt. The coming decade promises more than just better tools. It offers a new paradigm. We're moving from asking, "What are pulsars?" to "What are they for?" A shift as profound as realizing pyramids weren't just hills but tombs. With each technological leap, the line between natural wonder and engineered artifact blurs. Perhaps the greatest discovery won't be a message in the stars, but the realization that the universe has been speaking all along. We're finally building the ears to hear. You don't need a billion-dollar observatory to join the hunt for cosmic secrets, just curiosity and a little ingenuity. Amateur astronomers worldwide are tuning into pulsars from their backyards, using affordable radio telescope kits and open-source software to track these distant lighthouses. Projects like the Radio Astronomy Supplies Pulsar Hunter kit turn hobbyists into citizen scientists, capturing the faint whispers of neutron stars with equipment no more complex than a laptop and a homemade antenna. The barriers to entry have never been lower, and the potential rewards have never been higher. Open-source platforms like SIGPROC and Presto democratize data analysis, letting anyone sift through pulsar signals for anomalies. These tools, once exclusive to research institutions, now power home setups where enthusiasts can flag irregularities. A skipped pulse, an unusual frequency shift that might escape automated algorithms. Online databases like the Australia Telescope National Facilities Pulsar Catalogue put decades of professional observations at the public's fingertips, creating a global collaboration where a teacher in Oslo or a student in Buenos Aires might spot something a supercomputer missed. This crowdsourced approach is already paying off. In 2021, a German high school group analyzing archival data noticed a faint, repeating pattern in PSR J0945 plus 0801's emissions, a subtle echo effect later confirmed by professional astronomers as an interstellar plasma lens distorting the beam. Without amateur scrutiny, this insight might have languished in unexamined data. Similar discoveries are happening monthly, proving that the search for cosmic messages thrives when it's a collective effort. The beauty of amateur pulsar monitoring lies in its diversity of perspective. Professional astronomers often focus on specific research goals, while hobbyists explore freely, following hunches that defy conventional wisdom. Some track rogue pulsars with erratic glitches, while others hunt for ultra-faint millisecond pulsars overlooked by large surveys. Online forums buzz with shared techniques, from using software-defined radios to repurposing satellite dishes. It's a modern-day version of the 18th century, gentleman scientist tradition, except now, the lab is the cosmos and the tools are digital. Critics argue that amateur data lacks the precision of professional observatories, and they're not wrong. But history shows that paradigm-shifting discoveries often start at the edges. The first pulsar, after all, was found by a graduate student scrutinizing unusual chart recorder squiggles. Today's backyard astronomers have better tools than 1960s Cambridge labs, and they're connected in real time. When thousands of eyes and ears scour the sky, the odds of catching something extraordinary multiply. This isn't just about finding aliens, it's about redefining who gets to do science. Every submitted observation, whether it reveals a new interstellar phenomenon or just refines our understanding of known pulsars, adds to humanity's shared knowledge. The universe doesn't care if its signals are decoded by a Nobel laureate or a night shift worker with a passion for the stars. It speaks to anyone willing to listen. And as more people tune in, we're not just expanding the search, we're building a planetary ear, poised to catch whispers from the cosmos that might otherwise go unheard. Pulsars have always been more than just celestial objects, they're storytelling gold. When Jodie Foster's character in Contact tuned her radio telescope to the rhythmic pulses of Vega, she wasn't just hearing a star, she was unlocking a cosmic blueprint hidden in plain sight. The film, adapted from Carl Sagan's novel, captured the public imagination by blending real science with a tantalizing what if pulsars weren't just natural phenomena but deliberate signals. It's a theme that echoes through sci-fi history. Doctor Who took it further, portraying pulsars as time travel beacons or galactic SOS calls, while Transformers imagined them as energy sources for alien machines. These stories thrive because they tap into a deeper truth. Pulsars feel artificial. Their precision is unnerving, their persistence uncanny. fiction just dares to ask the questions science is still weighing. But pop culture's role isn't just entertainment, it's cultural preparation. Consider how the X-Files primed audiences for the possibility of government UFO cover-ups decades before official Pentagon disclosures. Similarly, Pulsar-centric stories normalize the idea that the universe might be speaking to us, just not in a language we've yet learned. When Interstellar depicted a wormhole near a neutron star, it wasn't just spectacle. It was a crash course in extreme astrophysics disguised as a thrill ride. These narratives act as societal dress rehearsals, softening the shock if science ever confirms that pulsars carry more than meets the eye. The irony is that reality often outpaces fiction. The real-life wow signal of 1977, a mysterious radio burst that remains unexplained, reads like a sci-fi plot twist, yet it emerged from cold, hard data. Meanwhile, scientists like Paul Davies seriously entertain the idea that pulsar anomalies could be technosignatures, proving that the line between speculative fiction and cutting-edge astrophysics is porous. Even the terminology overlaps. Astronomers casually refer to the lighthouse model to explain pulsar beams, a metaphor straight out of a space opera. What makes pulsars uniquely suited for storytelling is their duality. They're both predictable and enigmatic, reliable clocks with occasional glitches that defy explanation. This tension mirrors humanity's own relationship with the cosmos, a mix of awe and analysis. When Star Trek imagines a pulsar as a navigation marker for alien traders, or Mass Effect scripts it as a relay for ancient civilizations, they're riffing on a very real scientific proposition. Pulsars are the universe's natural GPS. The difference is sci-fi skips the peer review. Yet for all their creative liberties, these stories serve a vital function. They keep the public looking up, questioning, and wondering. Every time a TV show or film gets the science mostly right, like Arrival's linguist decoding alien symbols, it sparks real-world curiosity. Kids who watched Contact became astronomers. Doctor Who fans now pass pulsar data in citizen science projects. The cultural footprint of these narratives ensures that if the day ever comes when a pulsar's pulse carries more than physics, society won't panic. It'll lean in and say, "Tell us more." The greatest testament to pulsar's grip on our imagination, they've become shorthand for cosmic mystery itself. From video games to comic books, a flickering neutron star in the background isn't just set dressing, it's a promise. A promise that the universe is stranger, richer, and far more communicative than we've dared to dream. And sometimes it takes a work of fiction to remind us that the truth is still out there, ticking away in the dark. Mainstream science has a complicated relationship with bold ideas, especially when those ideas brush up against the edges of established understanding. When it comes to pulsars, the consensus is clear. They're natural phenomena, cosmic lighthouses born from the violent deaths of massive stars. But the moment you suggest their signals might carry something more, a whisper of intelligence, a deliberate pattern eyebrows raise, and the word fringe starts floating around like a cautionary label. Skepticism isn't just common in these discussions, it's baked into the scientific method itself. Extraordinary claims require extraordinary evidence, and so far, no pulsar has handed us a smoking gun in the form of an alien hello. Yet history whispers a counterpoint. Every paradigm shift in science began as a heresy. Galileo's telescope revealed Earth wasn't the center of the universe, a notion that cost him his freedom. Plate tectonics was once dismissed as geological fantasy. Even Einstein's relativity faced fierce resistance before it rewrote physics, the common thread. Breakthroughs don't come from nodding along, they come from daring to ask, what if we're wrong? Pulsar research is no exception. The first detected pulsar, CP191919, was almost mistaken for an alien beacon because its pulses were so unnervingly regular. That initial moment of uncertainty wasn't a failure of science. It was science at its best, questioning, probing, refusing to take the universe at face value. The tension lies in balancing rigor with imagination. On one side, you have researchers like astrophysicist Paul Davies, who argue that dismissing pulsar anomalies outright risks blinding us to potential discoveries. After all, if an advanced civilization were using neutron stars as cosmic radios, their signals wouldn't arrive with a flashing, made by aliens sign. They'd be subtle, layered into the noise, waiting for someone sharp enough to tease them apart. On the other side, critics rightly point out that nature is endlessly inventive. What looks like a coded message could just be physics we haven't untangled yet. The Crab pulsar's occasional glitches, for instance, were once mysterious. Now we know they're likely caused by starquakes or sudden shifts in its superfluid core. What's needed isn't less skepticism, but better skepticism, the kind that doesn't shut down curiosity but channels it. Think of the Laser Interferometer Gravitational Wave Observatory, LIGO. For decades, gravitational waves were theoretical, their detection deemed nearly impossible. But scientists kept refining their tools, and in 2015, they captured the ripples from two colliding black holes. The lesson, absence of evidence isn't evidence of absence. It might just mean our instruments aren't sensitive enough yet. The same could be true for pulsar signals. Projects like Breakthrough Listen are now applying machine learning to sift through decades of data, hunting for patterns too nuanced for human analysts to spot. It's a marriage of open-mindedness and precision, where algorithms do the drudgery so intuition can roam free. At its heart, this debate isn't just about pulsars, it's about how we explore the unknown. The universe doesn't owe us easy answers. If there's a message hidden in the spin of a neutron star, it won't be written in Morse code or English. It might be encoded in the quantum states of particles or the timing of glitches spaced across millennia. Decoding it will require more than bigger telescopes. It'll demand new ways of thinking. That's the tightrope walk of science, staying grounded in evidence while reaching for the stars. As Jodie Foster's character in Contact put it, the universe is a pretty big place, and if we're the only ones here, that's not just lonely, it's statistically bizarre. Pulsars, with their eerie precision and occasional mysteries, keep that wonder alive. They're reminders to stay humble, stay curious, and above all, stay listening. Because the day we stop questioning is the day the cosmos stops surprising us. Pulsars have come a long way from being dismissed as celestial curiosities to standing at the forefront of one of science's most profound questions. Are we alone in the universe? These spinning neutron stars, with their rhythmic pulses cutting through the cosmic silence, have evolved from mere astrophysical phenomena to potential participants in a conversation spanning galaxies. Whether their signals are the result of nature's ingenuity or the handiwork of an advanced civilization, they force us to reconsider how we listen to the cosmos. The idea that these distant lighthouses might carry messages encoded in their glitches, polarization, or even their quantum fluctuations transforms every pulse into a sentence in a language we're still learning to read. Consider the sheer scale of this possibility. Some pulsars have been beaming their signals for billions of years, long before Earth formed. If even one of them carries an artificial signature, it would mean the universe has been bustling with activity for eons, quietly waiting for a species like ours to develop the tools to decode its whispers. This isn't just about finding aliens, it's about discovering that the cosmos might be threaded with meaning, a vast network of communication hidden in plain sight. The implications are staggering, reshaping not just astronomy, but philosophy, linguistics, and our very sense of place in the universe. Yet the challenge remains immense. Deciphering a potential message requires more than advanced telescopes. It demands a fundamental shift in how we think about communication. Human language is linear, bound by time and syntax, but an interstellar signal might operate on entirely different principles. Imagine a message encoded not in words or numbers, but in the gravitational interplay between binary pulsars or the quantum entanglement of particles within their beams. It's like trying to read a book where every page is written in a different dimension. The breakthroughs needed to crack such a code could revolutionize technology, unlocking forms of data transmission we can't yet fathom. For now, the pulsars keep spinning, their signals unwavering. Each new observation peels back another layer of mystery, whether it's a millisecond pulsar defying rotational models or a glitching neutron star hinting at unseen forces. Projects like the Square Kilometre Array and next-generation quantum sensors promise to amplify our cosmic hearing, turning today's faint whispers into tomorrow's clear dialogue. But the most exciting prospect isn't just technological, it's cultural. The moment we confirm a pulsar signal isn't entirely natural would unite humanity in a way few things ever have, transforming us from isolated observers into active participants in a galactic exchange. So as we gaze at the night sky, let's remember, those steady pulses might be more than dead stars ticking away. They could be invitations, archives, or even alarms, echoes of a universe far more connected than we've dared to imagine. The question isn't whether the stars are speaking, but whether we're ready to join the conversation. What do you think? Could pulsars be the universe's oldest messengers, or are we reading too much into the cosmic static? Drop your thoughts below, and if you've enjoyed this journey through the silent language of the cosmos, hit subscribe for more explorations into the unknown. The next great discovery might be just one pulse away.